SMJP 1022 Material Science, Chapter 6 Phase Transformation. In this chapter, we will cover into two parts. Part A, which is phase transformation and phase equilibrium. Part B gives phase rules and construction of phase diagram. In this part, we will cover phase transformation and phase equilibrium. Basically, we will go for the definition and basic concepts. So in this beginning, we will cover the terms related to this chapter. Phase is a portion that has homogeneous and uniform chemical and physical properties in a system, which is related to the physical properties, which is mass, volume, density, and etc. And then for the phase boundary, a surface that separates a phase from the other in a system. So it's kind of separating in two system or three system. Homogeneous, which is a small part of a phase, cannot be differentiated from another small part in the same phase. So there are phase in homogeneous and non-homogeneous, which is the homogeneous, which is all over the place in the phase is the same, whereas the non-homogeneous is not the same for the whole phase. And then for the solution is a mixture which forms a single phase, such as salt water. We have a mixture of salt and water. The salt will dissolve in the water, whereby it will dissolve in the single phase, which is water. For the solid solution, a mixture which is a solid. So for the brass is a mixture in the copper and zinc. So the combination of solid copper and zinc produce a brass. This is we call it solid solution. And then solubility, we have dissolving one phase in another and retaining only one phase. And then we have a solubility limit, the maximum amount of one phase that can be dissolved in another. And finally, we have a weight percent, which is a usual measure of phase. Let's say if you have a 70-30 brass, that means we have a 70 weight percent of copper and 30% weight of zinc. So the combination of the position of different weight, but in terms of percent. Okay, for the copper we have 70, and for the zinc we have 30% weight percent. And if we go for the like a gram or kilogram, let's say we have 100 gram of brass, it means that we have 70 gram of copper and 30 gram of zinc. Okay, along the way, later on, we will discuss more on the concept of phase diagram. We will cover all those terms. So next, we have a different phase. If two portions in a system having different chemical and physical properties, different of composition and crystal structure, that means we have a composition of mixture in terms of a solid solution of different materials such as uh, copper in percentage and zinc in terms of percentage, and combination of copper, nickel, plumbum, zinc or something in composition, and it will produce a different structure of combination in terms of uh, big small nucleation related to the uh, growth of nucleation. And for example is a solid, liquid and gas phase, and we have let's say we have ice and water in combination, which is the same composition, and produce a different structure whereby water is in liquid phase and ice in the solid phase. So it will have two different phase, okay, in the same system. Crystalline solid can exist in several different phases. So different ways of combination of atom, like we have a combination of phosphorus, tin, and ferrous iron or something in combination. Okay, and if this combination basically will produce a alloy. So after this, we will look at the different alloy, okay, in combination of elements. And then system, which is may contain one or more component, and then may consist of solid, liquid, gases, or their combination. It may be combination. We have a solid and liquid, okay, and then liquid and gas combination, okay. So and solid gas combination may contain metal or non-metal individual or in combination. Okay, this is the element of metal element mixture with the non-metal. May refer to a specific body of material, okay, separates from its surrounding. The system also subjected to change of composition, temperature, pressure, volume, and etc. So it will become a parameter of in the system whereby we fix the temperature. We will look at the composition or pressure difference, or we fix the pressure at several at number of atm, and we look at the composition whereby we increase the temperature or decrease the temperature. So we will look the system will change according to this parameter. And then for the equilibrium, which is the dynamic condition of physical and chemical, which appears to be a condition of rest rather than one of change. So this is related to the stability of condition in terms of physical and chemical properties of material. it will describe in terms of free energy, which is in equilibrium. The atomic will behave in terms of kinetic energy or energy stored in the system, so that we will look at the free energy, which is a function of system internal energy, function of atomic randomness of the order, whereby if we have compare with the solid, liquid and gas, so it will have a different free energy. In terms of gas, there is more energy than solid and liquid. So it will discuss on the internal energy, okay, in the uh, steam or gas. And then for the in term of the kinetic energy or movement of atom, if compared to the solid and liquid, gas is more disorder or random, uh, show the behavior. And then we have phase equilibrium, phase at a minimum free energy under certain combination of temperature, pressure, and composition. Okay, in this case, we have a phase equilibrium, whereby we have three phases, which is solid, liquid, and gas. In the equilibrium, whereby the parameter change them in terms of temperature, pressure, and composition. Phase characterization do not change with time. Okay, if temperature, pressure, or composition are changed, okay, this free energy will increase. Okay, and it will change to other state. Phase to lower is free energy. Okay, and then we will go for the phase diagram. Okay, we discuss more on the uh, phase diagram, or we call it equilibrium diagram. So every element or metal behave or will change to it phase diagram. Okay, it will show the behavior of uh, kind of relationship between phase in equilibrium as a function of temperature, pressure, and composition. This, as you can see in this schematic diagram, there is a change in terms of temperature and composition, whereby temperature is in y-axis, and we have a composition in terms of weight percent in x-axis. Okay, whereby here is a pressure is a keep constant, and when the temperature increase at the composition constant, we can see a slightly different in terms of graph. Okay, in white, in red color, change, okay, or decrease or increase. Okay, in this case, the phase diagram act as a map to project the relationship between phase in equilibrium. Along the way, we will can gather more information related to the microscopic nucleation takes place at a different spot. Okay, this is a map helpful in predicting, basically in the phase transformation. Okay, we can project what is happening when the composition we mix at the different percentage. Okay, and it will result the microstructure. Okay, we can predict what is happening at the certain spot, what is the size of microstructure, what is the existence or present of a solid or liquid or in combination of two materials. Important to understand phase diagram is produce a strong correlation between microstructure and mechanical properties. Okay, once we understand the microstructure, so that we will make some kind of study in terms of its mechanical properties, okay, whereby mechanical behavior is depend on microstructure. So in the previous chapter, we already discussed on the um, effect of the microstructure uh, in terms of green growth or something in order to make it strengthening or strengthen the metals. A microstructure is characterized by a number of phase present. They are proportional. Okay, the phase present is whether is in percentage number. Okay, in term of solid or liquid or combination of solid liquid or their proportion, the percentage, okay, and their distribution of arrangement. It is a powerful tool for science and engineer, okay, which is they want to design a product for specific application, so they need to study to look at the behavior of these materials, anticipate steady of materials, stability of materials. So that among important use of phase diagram, predict phase in equilibrium for certain alloy composition at desired temperature. So that maybe we have a certain composition of alloy, and then at the certain temperature we want to project what is happening in terms of phase equilibrium. Determine chemical composition of each phase and also calculate the quantity of each phase. Predict phase transformation when subjected to slow cooling or heating. And determine microstructure as a result of phase transformation. Okay, this is a 2D phase diagram. Okay, we have a y-axis and x-axis, whereby we have only two types. Okay, showing the phase boundary and color code phase region, whereby we have a temperature composition phase diagram in left hand side. This is the one is a aluminum silicon alloy phase diagram. We can see something like for the temperature is a y-axis, and we have a composition in weight percent at a x-axis. And another one is a iron carbon phase diagram, the complete set in terms of different changes in the temperature versus the composition of iron percent and carbon in terms of percent. Okay, which is the two materials combined together and become a alloy. So it will show the phase diagram is something like this. The another one, we have a pressure temperature phase diagram, which is indicates the y-axis is a pressure and x-axis is a temperature. So this is a two phase diagram from the CO2, and we have which is carbon dioxide, and another one is we already know there is a water phase diagram. So it will project with a different characteristic of mapping in terms of different phases change at a certain temperature or at a certain different pressure. From there, we can project or we can manipulate so that we will have a different characteristic at a different point. So phase diagram, basically we will try to look to study at the phase diagram in these cases when phase diagram display the state of a substance at a various pressure and temperature and a place where equilibrium exists between phases. Okay, here is a kind of a phase diagram, but previously we learned in chapter 3, okay, related to the uh, solid liquid transform, okay, where need to introduce melting, freezing, and liquid to gas where it will vaporize, or gas to liquid it will condense. Okay, here in this different kind of diagram, it will show the phase transformation or phase equilibrium in term of diagram here, whereby we have three phases at the same map, and it will produce a phase boundary. We have like AD is a phase boundary between solid and liquid. AB line is a phase boundary between liquid and gas. And also we have AC whereby a solid and gas boundary. Okay. So we already know the atomic arrangement of different phases. Okay. So if we want to discuss more about the uh, this is actually a water phase diagram, okay, or water equilibrium diagram, whereby we have a solid, liquid, and gas. And if we discuss more on the liquid vapor interface, which is a AB line, we have A is a critical point, and at B we have a critical point. This is the, we call it, in A point we have a triple point, which is whereby three phases coexist at the same time in equilibrium. And B we have a critical point, whereby the highest value of pressure and temperature uh, border of the liquid and gas. And then for the line AD, which is a solid liquid interface, the melting point of each pressure can be found along this line. And below A is a substance cannot exist in the liquid state, so that the phase only exists along this whether solid boundary and gas. Okay. At this area, the behavior or the phase will not turn to liquid. And then for the solid gas interface, we have a AC line. Okay, this one already discussed. Okay, Okay, if we discuss more on the specific line, so that at the in term of this water, we have in solid phase we call it ice. Okay, in liquid phase we call it water. So if we fix at 0 degrees Celsius, of course we have the line, okay, project to high in term of higher ATM value or pressure value. Once we increase the pressure value at a specific temperature, we will have we will look at the phase changes in term of number 1, number 2, number 3, number 4, and number 5. So for the case of point 1, at low temperature, uh, at point 1, H2O exists totally in vapor. And when the pressure is increased at point 2, we will have a solid vapor equilibrium exists. And once it increase of temperature higher at point 3, we have all the H2O is converted to solid. It become ice, complete ice. Okay, 100%. So and then at point 4, some of the ice will melt and equilibrium. Okay, between solid and liquid is achieved. Okay, at that time, at that point, ice and water at equilibrium. Okay, and at point 5, at higher pressure, all 100% ice will transfer or become a water. And it also happen at point 6, 4, 7, 8, and 9. Okay, whereby at point 6 we have H2O is basically in solid or in ice, and at 4 is a intermediate phase boundary, whereby the existing of ice and water in equilibrium. And at point 7 we have a completely water, and at point 8 we have a equilibrium of water and steam or gas. And finally at point when we increase temperature, okay, at certain degree Celsius, it will totally convert the liquid to gas in 100%. Okay, so that here we can if we have a phase diagram, and then we can make some analysis in term of phase changes. When we keep the x value fixed and let the y value increase, is what happening in this case. This line of 1, 2, 3, 4, 5 will change, and also we can see the what is happening when we change the temperature from the lower degree Celsius to higher degree Celsius at a y-axis constant. Okay, whereby here it will set at 1 atm constant. So from there we can make some analysis in terms of phase changes, and also from the microscopic point of view. And this is for the water only, but we will see a different of material composition. Okay, a combination of two materials. Okay, so we will make some analysis from there. So for the next slide is a classification of phase diagram, whereby we have three types of phase diagrams. basically the three type of phase diagram is based on number of component in alloy system. So that for the single component, okay, we will call the unary phase diagram, okay, whereby we have x, y axis is the pressure, temperature phase diagram, and then we have two components. We call it binary phase diagram. We have temperature composition phase diagram, and different type of phase diagram. We have three components, which is ternary phase diagram. Okay, for the differentiate between three of them. Okay, basically for the component system, we have single, two component, and three component. And then variable, basically in the unary single phase diagram, only covered for the pressure and temperature. Okay, no composition, whereby the composition of a mixture between two material is not uh, state there. Whereby the binary phase diagram, we can see two component. We have a pressure, temperature, and involved with the one composition. Okay, for the ternary phase diagram, we have two composition and temperature. Okay, but this one is quite complicated phase diagram. And then for the plotting phase diagram is basically the phase diagram for the unary is something like water CO2 phase diagram. For the binary phase diagram, we have basically the changes effect on the temperature, and we want to see from the composition, whereby other parameters such as pressure, it will keep constant. Okay, for the ternary phase diagram, basically we will see in the 3D space model, and this one is quite complicated. But basically in this chapter, we will cover only a binary phase diagram. Okay, and then we will go for the construction of phase diagram. Okay, how we construct basically the phase diagram, we just see from the previous slide, which is we have a unary phase diagram, uh, and this is from this phase diagram. Okay, how we construct there. So basically, if we have two composition, whereby the mixture from the two different material. Okay, in this case, we will see different material of copper. Okay, mixed with the nickel. So in terms of composition, we will in this case we will divide into three composition, four composition, which is from the 100% copper. Okay, whereby the zero nickel, okay, present. We have 20% of copper, 80% of copper, plus 20% of nickel, and also we have 40% copper and 60% of nickel. Okay, we can see the once we increase the temperature, okay, or we heat the mixture at 100 copper, zero nickel, and let it dry, let it cool, and it will take some time in order to cool it, and we can see this kind of graph produced. It also happen from the 80-20%, it will something like this, and also we will project the different line graph here. And finally, in the last mixture, last composition, we have 100% nickel. It will behave is something like this. So basically, if we'll test more composition, let's say 1% copper, 99% nickel, 5% copper and 95% nickel, and the various information we can produce here. So basically, uh, from this we can see a point difference here, whereby we have a point A, point B, A1, B1, A2, B2, A3, B3. So if we have so many lines, so we can see different changes in terms of A and B, and then we can see the projected line. Okay, if we connected all together, so and it will become a pattern. Okay, so basically pure metal, we know the solidification occur at only one temperature. Okay, cooling curve for pure copper and pure nickel. Okay, at we can see from the 100% copper and 100% nickel, and what is happening if we change, so that this alloy takes place, alloy, and it will have a range of a temperature graph. Okay, and the various of composition, and finally we will see a quite interesting a line. So this line we call it liquidus. Okay, whereby the liquidus is the upper line if compared to the solidus line, is something like this. So during the construction of this diagram, basically it will the experiment or test, a lot of tests happen in the different temperature and different composition. So and finally this complete map of the composition in terms of different temperature we will produce. Okay, and we can see from uh, this is the phase diagram of the nickel, copper nickel composition, complete set from the 0% nickel or 100% copper until 100% nickel and 0% copper. So the uh, line of the liquidus and solidus is placed is something like this, whereby we can see from the projection, if we want to look at the analysis in terms of uh, composition fix, okay, so that we can project to get the temperature. Okay, and then at the temperature we set, and then we can project to get the composition. Okay, for the liquidus, basically you are showing temperature at which alloy begin to solidify. So this line basically uh, separated, okay, or we call it phase boundary of liquid and liquid solid. So in here we have a solid liquid mixture, okay, whereby the place is in here, okay, whereby the solid liquid mixture and is separated from this line, whereby we call it liquidus. At this upper region we call it liquid region, and below this line we have a solidus line, whereby the consists of solid, okay, solution here, whereby the solution of solid mixture with nickel and copper in here, okay, but in solid phase. For the solidus, it's basically showing temperature at which alloy becomes solid completely. Okay, can represent in this red color. Okay, construction result basically very tedious work to do, because it will involve with the experimental works. Okay, you need to make testing in terms of different composition from 1% copper, 99% nickel, and we have a various data, and then finally it will we compile, and finally it will produce a very solid phase diagram. In this case, we have copper nickel phase diagram. Okay, and then some of the phase diagram at a certain temperature or certain composition, it will behave or will show a different or tiny or small detail, so that very special or unique characteristic of materials. Okay, so here we will cover the copper nickel phase diagram. So actually, from the previous construction of phase diagram, we already use a example of copper nickel phase diagram. So in this case, we will more explore on in terms of analysis of the copper nickel phase diagram. Okay, determination of phase present and phase composition. So we will look at the phase present in certain area of intersection line of let's say we want to look at the composition of 40%, 60% of this composition intersect line with the different temperature set. Let's say we have 1205 and 40 nickel 40%, and we will see from the intersection is here or which area. So we want to look at the present of phase and then for the phase composition. Okay, this one we will locate the temperature composition point, and we will note the phase field, and let's say we will look at the 60% nickel and 40% copper at 1100 degrees Celsius. So basically we will make intersection of two lines at point A, whereby we have the basically at point A is in the region of solid solution, whereby the existing of percentage of 60-40 nickel copper in the solid phase. Okay, so the symbol we will use here is a alpha phase, so that's mean it will represent for the solid phase. And also if you look at the 35% nickel, 35% copper at 1250, this point become a point B. So here there is a mixed phase here in liquid and solid, and for the symbol maybe we can write as alpha plus L. Okay, L stand for liquid and alpha stand for solid. And if you want to look at the very details, so maybe this phase diagram we will make it a small box to zoom in a little bit and to look at what is happening at the composition. Okay, something like this. So whereby we can see if we add a certain temperature, okay, line, let's say we have this line. Okay, at this certain temperature line, we project along this line, and we have two point intersect with this point and also this point along the line at B here. So these 2 point intersect and we project to the y-axis and it will produce a point here whereby the composition, okay, maybe 32, 33 composition of nickel here, and also the point intersect in here whereby it will produce C alpha. So here the data in another data that we can produce, okay, we have a point B at C0 here, and we can see the value of this region R and S. So we can calculate the value of R and the value of S here. Okay, for the determination of phase composition, okay, basically in one phase region, basically in one phase region is we call it this area is one phase region, okay, liquid, and this area is one phase region is solid. This is a two phase region, okay, actually alpha and liquid here. Okay, same as composition of alloy. Okay, let's say when we this one is a example of point A. Okay, we have 6040. Okay, and then for the into two phase region, we have we need to construct a line. Okay, so that there is a 2 point intersect from I explained previously. Okay, we need to note that intersection phase boundary on other side, and also draw a vertical line on both two sections, and from there we will read the composition in terms of R and S. Okay, and then for the determining the phase amount, basically the amount of composition, whether the amount of in weight percent of nickel and copper. So basically we will look at the this intersection point. We have a Cl, Co, and C alpha here. This value can be calculated in term of to get the number of R and S. Okay, and then relative amount of fraction of percentage. Okay, whether we calculated this number of we get R value and S value in term of the fraction of in term of percentage. In single phase region, basically we have uh, of course we have fraction of 1 or 100%. So in liquid on phase region, let's say in this area we will have 100% liquid, and this area we have 100% solid. But in this area there is a how many percent liquid, how many percent solid is depend on this line. Okay, so basically uh, in two phase region we need more calculation, but it will involve complex but not difficult, but more complex in term of percentage. Okay, cannot straight away we get the value, but we need to have a certain formula to calculate. Okay, this is whereby the level rules come in to help this to get the composition of the phase amount. And for the lever rule, okay, basically lever rule is a tools used to determine weight percentage of each phase of a binary equilibrium phase diagram. It is used to determine the percent weight of a liquid and solid phase for a given binary composition and temperature that is between the liquidus and solidus. So how we will get the value of this composition or phase amount? So basically construct a tie line, okay, across region at temperature of alloy. Basically this one I already explained. And get the fraction, whereby the fraction is indicates the R and S, okay, and get the value, okay. If we want to get the R value, that means the CO must be minus CL. In terms of S value, we need to have C alpha minus CO. So we will get try to get the phase fraction. Okay, let's see at the point B. We have the presence of liquid and solid, and the overall alloy composition at B is basically CO, and then alpha phase composition at C alpha, and then we have liquid phase composition at Cl. So and then we have R, and then we have fraction of S. Okay, basically in the phase diagram, okay, if we given the phase diagram and we have the value of x-axis, so that we can make a projection to the C alpha, CO, and Cl. In this case, let's say we have Cl 32%, CO 35%, C alpha 43%. So in order to get the alpha phase fraction or WA, W alpha, the value is something like this, okay, whereby the R divided by the R plus L. Okay, and for the liquid phase fraction, WL, so this value, this formula we will use S minus S divided by R plus S. Okay, for the mass fraction, we have this value. So we have finally we have C alpha minus CO divided by CO minus Cl. Okay, specified composition in terms of one component. Okay, for the CO, we have 35, C alpha 43, Cl 32. So in terms of from the lever rules, so the WL we calculated and we get the value of 0.73, and for W alpha we have 0.27. So the total of these two should be 1, or in term of percentage, you can make it in term of WL 73% or WA in 27%. The total in percentage will be 100%. Okay. So this is the way to get the amount of percentage in term of alpha and liquid fraction. So by using the lever rule, we can identify the value of WL and WA, W alpha. So I think from the given different phase diagram, we will able to get this value. Okay, thank you very much. Bye bye.